Hello. In this session, we discuss about electromagnetic wave propagation. The topic is wave propagation and lossy dielectric medium. A lossy dielectric medium is medium in which an electromagnetic wave loses power as it propagates due to poor conduction. Actually, this lossy dielectric medium wave propagation is a fundamental to understand different wave propagation mediums. For example, to understand wave propagation in a good conductor or wave propagation in a lossless medium. So wave propagation in lossy dielectric medium is this. So if you know or if you understand clearly this wave propagation in the lossy dielectric medium, we can easily derive this remaining on. Now let's see. Now we consider a linear isotropic homogeneous lossy dielectric medium. And I said that lossy dielectric medium. So lossy dielectric medium is what? The lossy dielectric medium is a medium in which electromagnetic wave loses its power due to the imperfect dielectric property. Here we assume that lossy dielectric medium is a charge-free, and assuming and suppressing the time factor e power j omega t, we can modify the Maxwell's equations. Let's see that. Here I have given Maxwell's equation in two different forms. So point form and integral form. So del dot ds is equal to rho vs, del dot b is equal to del cross E is equal to minus j omega bs, del cross Hs is equal to Js plus j omega ds. So here we are assuming time factor is e power j omega t. In this table, I'm going to modify with the assumption that the concerned lossy dielectric medium is charge-free. If it is charge-free, so del dot D, we know that D is equal to, we can write it is D is equal to epsilon E. B is equal to epsilon E. The same way del dot B is equal to mu H. So in this, we apply these conditions so that del dot D becomes del dot ES is equal to 0 because it is a charge-free we assume that this lossy dielectric medium is charge-free. So that del dot ES is equal to 0, del dot HS is equal to 0. How we got del dot HS? B is equal to mu H. Del cross ES is equal to minus j omega mu HS. Here. So BS is equal to, so B is equal to, so B is equal to, so mu H. So by substituting this into this, so we get a new modified Maxwell's equation is here. So now I'm taking, for example, I'm taking the equation 3 here. Okay, now I'm taking call on both sides of this equation 3. So del cross ES, if you take a call of these 3 equations, now it becomes del cross ES is equal to minus j omega mu del cross HS. And by applying vector identity, that is del cross A here in this. So del cross A is equal to del dot A minus del square A. Here the vector A is nothing, that is E, that is electric field. So after applying call on both sides, and vector identity, then we get the equation is, so here it is del dot del ES minus del square ES. From this, here I'm making vector A is nothing, that is electric field. So it is here. So it is minus J omega del cross Hs. So in the place of del cross Hs, so here in this place of del cross Hs, so here we have a del cross Hs. So del sigma plus J omega epsilon Es. So substitute this equation 4 into this. And the del cross E is by vector identity expanded. Then we got these equations. And del dot ES is 0, we know very well. So that finally we get del square ES, that is after rearranging these equations. So del square ES minus this term we consider as del square ES minus, we consider as a gamma. So that it is del square ES minus gamma square ES is equal to 0. So here, this gamma square is equal to J omega mu sigma plus J omega epsilon. Here, this gamma is a complex parameter. Let's say that this gamma is a propagation constant. If I say that it's a complex parameter which consists of two basic parameters, that is alpha and beta. That is alpha is attenuation constant, beta is phase shift constant. Now see that here we had these equations, that is in terms of electric field. The same way, if we are taking call on equation 4, if you take a call on equation 4, then you will get result is del square Hs minus gamma square Hs is equal to 0. These two equations is called as Helmholtz equations, or simply we can say vector equations. Now let us take gamma is equal to alpha plus J beta. I said that already. So alpha is attenuation constant, beta is phase shift constant. So if you take a real part of this, there is a magnitude of real part of this. So this is equal to omega mu under root sigma square plus omega square epsilon square. So now we get from this alpha is this value, beta is this value. See here, without loss of generality, we assume that a wave propagates along positive z directions, and that electric field has only an x component. So now we can write it is. Now we can write it is. Now we can write it is electric field is, which is a z directions that has only x component. That means it does not vary in x and y directions. Only it is in z directions. So the medium is unbounded medium following z directions. So we can expand these equations like this. See here, I say that this wave has no x and y variations. So that x component, y component, that is the directions, becomes 0. So only component in z direction is available. So from this, we get a scalar wave equations. So from this scalar wave equations, we will understand that different frequency components in a wave travel with a different velocity, which causing a dispersion effect. Because so velocity u is equal to omega divided by beta, which can be equal to 1 divided by mu epsilon under root. So we can expand these equations. That is the linear homogeneous differential equations like this. So u of z comma t, which is equal to e naught e power minus alpha z cos omega t minus beta z in x directions, a z. So how we got this term? How we got these terms? Because from these equations, so we can write it is, so electric field in z direction is equal to, so it may be in two directions. That means positive z directions, negative z directions. We prefer only in positive z directions. So we consider these equations. So electric field in z direction is equal to E naught e power minus gamma z. So gamma, we know that that's the propagation constant. If I take a real part of this, so gamma can be written as alpha plus j beta. So substitute this into this. And if it is in negative directions, this term becomes 0. So only this is available. So E naught and E naught dash is nothing, it's a constant. So now we take this E naught e power minus gamma, which takes alpha plus j beta with the z. And we are taking a real part so that it becomes, so E naught e power minus real part means alpha z cos omega t minus beta z is. Okay. The same way we can derive the equation for a magnetic field. So this is the equation for magnetic field. And we know from intrinsic impedance. So intrinsic impedance eta is equal to, so E divided by H. From that we can write here these equations. And eta is a complex quantity known as intrinsic impedance of the particular medium. Now I can write this eta as a magnitude. So this is the eta equations. And in terms of eta, we have rewritten this magnetic field.